So I'd like to introduce Sumanta Chatterjee. Many of you know him. So Sumanta, just like to tell everybody in the room that at the very start of OpenIB, when Steve Poole and Matt Leininger and I joined the Intel meeting that Jim and others were in, Sumanta was sitting there way back in 2004, very quiet, right? But you've had a huge impact on OpenIB and Open Fabrics, and we really want to thank you for it, and looking forward to your presentation.
Thank you, Bill. You're very kind. But before I get going, a couple of things. My colleague Anna Soria from Oracle Corporate Marketing, she actually has a gift to give away at the end of my talk. So if you have not put your card, please put it in that little jar she has, and we'll pick one winner. DK was the winner last year. DK, last year you got a Kindle. This year we have upped it to an iPad. So it is one. Sorry, that's all was there so it is one. But anyway, whoever wins it, don't put it up in Craigslist. Okay. So the talk today, I'll be giving it, will be given by my colleague Rick Frank, and so my part of the talk will be a little boring, so I will go through this quickly. Let me see if I can work this. Okay. Yeah, so that's the standard disclaimer, right, which I've skipped. So the outline of the talk will be, I'll quickly go over the evolution of Exadata since I spoke to you last, and then we will do a quick thing about what the current models are, what we are working on immediately, and then Rick will actually give you some more details on what he's planning to do in the forthcoming year. So the most interesting thing that in Exadata front that we are offering right now is an 8-socket Exadata full rack database machine. The most interesting aspect of this, apart from we are offering this as a online transaction processing system and a great way to consolidate many databases into one system. Apart from that, from this body's perspective, this is the first machine that we have where we have got more than one InfiniBand card on a system. So each of these racks have 2 8-socket systems, and each of the systems have got 4 QDR InfiniBand cards. So these machines are performing really well, and they are obviously in fairly big demand. So throughout the course of yesterday and today, we have heard many people discuss the agonies of managing InfiniBand clusters and all the pains and so on and so forth. So one of the value add that we are trying to do is to sort of contain the pain. The pain comes to us, of course, but as far as the user experience is concerned, we try to contain it to the extent that we can. The other offering is, of course, with a 2-socket. Here we have got an 8-node cluster, and these have 1 card each, and there are 14 storage cells. They also have 1 card each. So this is a variation in the Exadata offerings that we have today. And by the way, this is the X22 rack is what is used mostly in our data warehousing deployments. Okay, so one of the interesting thing is that we are selling these racks for a couple of years now. And initially, people were buying maybe a quarter rack or a half rack, or some people were buying full racks. So the interesting thing is happening is that in many of the customers are now are asking us to build multiple rack solutions for them. So this is a very positive development from my side, because it is a validation of the InfiniBand architecture, the technology that you folks in this room have developed, and I can only express my gratitude towards you for building such a cool technology. Now, moving on. So here is, actually we use a factory architecture, and we can connect up to 8 racks seamlessly. Of course, this comes nowhere close to the picture that Bob presented yesterday, of I don't know, 10,000 nodes and so on. But within this modest configuration, the challenges still remain, and we are trying our best to cope with it so that the customers do not have to have the any brownouts or any kind of disruptions in their production system. Okay. Then, a couple of more words on the current operational model. So, as you know, we have an RDS kernel module driver that is built and bundled with OFED, and these are used for our cluster communication as rack messages. But the real use for RDS is in our Exadata, in the IO path. We use RDS for moving data from our storage cells to the compute nodes. We have also made some enhancements in our socket interfaces. I've requested, you remember a couple of years back about using the atomics and so on. So we are using the atomics. We are using RDMA read-write operations, and we definitely are the biggest cheerleaders for FMRs. Thank you, Tipperette, for doing this for us, and it is a lifesaver as far as I can tell, because we can do millions of them without blinking an eye. So it works for us. I notice, and within this topology, as you can see, we are getting, great performance. We can do millions of IOPS and with over 4 HCAs. So these are all, great things, and these directly translate into query processing, the times, and the kind of things that people can do. And you probably have seen our advertisement everywhere in the world. You can't escape it. So, but a lot of it is true. And so, again, thank you very much. So, moving on, the current status, we have got, we have certified RDS over TCP. People wanted to do this, so you can actually use a regular gigabit Ethernet card, and you can use RDS because, again, what it does, it makes our stack lot simplified. So we are very so this particular certification was done late last year. We are validating Rocky as we speak, and we are doing ongoing work with RDS driver. Of course, in the 8-socket system that I talked about, it is a very serious NUMA system. So we had to do a bunch of work to make our system NUMA aware, and we had to have NUMA affinity for our HCAs and how we do IOs and so on. We had to do a fair amount of work in the Linux kernel to do the interrupt balancing, and there are all these other enhancements like order hinting, shared receive queue, and resource reuse pre-allocation. So these are all things that our Linux group has put in so that the database can work very nicely in that environment. Okay, one other thing I just wanted to quickly touch upon is that we are working on user mode NFS client, which we already have, but that was running on top of TCP. But we have implemented NFS RDMA in user land. And right now, this particular offering is not yet in production, but we expect to see it shortly. We are validating our code with our son's S7000 series machine. Now, I'm sort of trying to rally all the NAS vendors to actually support NFS RDMA, but the only person I could convince is a person from Sun. I haven't been able to convince others. So if you have any influence on NetApp or EMC or whoever who is building NAS storage, please tell them that NFS RDMA is a cool technology. They should embrace it. It improves performance. It saves CPU and all the other good stuff. Okay, so now I will hand it over to Rick. He's going to talk about all the new things that we are building.
Show me how to use this.
And just press this one.
Yeah. So RDS is something we started many years ago. You guys have seen me up here before. We eventually actually put it in production. And just to put some numbers around it, I think we're selling something like 2,000 systems a year. 40 or 50,000 of these NICs are going out in these systems. And it just performs very, very well. But we also learned quite a bit about what it means to use RDS. It solves some problems, but it creates other problems. Some of the problems that we see are when you're running a million IOPS, the other thing is that you're consuming a lot of kernel time just doing message processing. You're interrupting the systems to death. At 1.7 million IOPS, we're actually consuming 4 cores just in interrupt and driver processing, which is just absolutely enormous. It has a big impact to the system, especially if you're not careful about balancing those interrupts. You get a few cores that are lopsided, extremely saturated. You have to make sure you steer all your user mode processes away from those, because then they slow down and you get very lopsided response times that basically swamp the system. So some of the work that we are trying to do is, while we continue to use RDS for our I/O systems through Exadata, we're also trying to shift some of our communication away from RDS in our rack environment, because we have very, very latency-sensitive applications that want to do distributed buffer cache management in a rack cluster. And so tying them to the same backbone that it has a million IOPS running through it, you just get long latencies, uncontrollable latencies. And the messages that we're talking about for I/O are anything from 8 kilobytes up to a megabyte, where the messages that we're pushing through between the rack nodes are very small, anywhere from 4 bytes up to maybe 256 or maybe 400 bytes. So they're very, very small messages. So we have the kind of characteristic problem that was talked about earlier, which is you really have to be careful about controlling latencies when you're trying to push the different size messages down the same paths. And so we've done a lot of work inside of the IPC at Oracle. We've factored it. We cut out 75% of the code, and we've introduced more of a modular system where we can run multiple different transports. We started out with UDP, believe it or not, 5 or so years ago, and we shifted to RDS for just about everything that we do inside of Oracle. But we're now introducing a couple of user mode transports based on libIB verbs, an RC transport, and an XRC transport. And these all fit seamlessly under an Oracle IPC, which is what the entire Oracle database uses. So once we turn on one of these transport, it's 100% transparent to the rest of Oracle that we're running on top of it. We greatly simplified our Oracle IPC interface. I like to say that we dropped the MIT effect. The person who actually architected the interface is now actually a senior executive vice president at Oracle, so he did something right. But it was a completely complex interface, and by simplifying it, we were actually able to drop quite a bit of the code out of it. And so we get 50% shorter code paths while running through this thing, and we can run on multiple different transports. But the most appealing thing is that RDS is really a message event-based message system. And all of Oracle's communication was really based on messages. And even when we run on Exadata, a lot of the communication is still based on messages. Even though we run a storage protocol and we ship off a small message and we might initiate some RDMA operations, it's still all event-based. And we all know that the real advantage to RDMA is the fact that you can silently reach into a remote system and you can play with this memory. You can read data out of it, you can push data into it, and you can do it completely bypassing the kernel. You can do it with no interrupts. And so the opportunity exists, as was been talked about many times today and yesterday, is that you can push data and you can read data without actually having any interaction of a remote process. And so you can get completely away from the event-based model, which is jump into the kernel, send a message over the wire, take an interrupt, push it into a socket, wake a process up, get it to read the socket, and then do the reverse to send the entire thing back. That might take 20 microseconds, where if we can deliver messages bypassing the kernel, not generating those interrupts, using RDMA, we can directly place them in the memory. And so that's really where a lot of the work is going. We're moving away some of our, from the event-based messaging. We're going more towards an MPI-style busy wait model. But in order to do that, first let me set a little more context. Oracle is a time-sharing environment, and we heavily over-provision our CPUs. 8 cores, we might run several hundred processes. They're all doing time-sharing. They're all doing messaging. They're all doing I/O. They're all synchronous processing. Causes a great deal of context switching. You get deep scheduling queues. So if you release a CPU as one of those threads of execution, you don't know when you're going to get it back, just because there might be 30 other tasks sitting in front of you to get it back. So what we want to do is try and not release that CPU, but the only way we can efficiently do that is to have very short latencies, so you can afford to busy wait while you're waiting for a response. And in our investigation, we think that an acceptable busy wait time is something around 5 microseconds, ideally something less than 5 microseconds. So we want to do operations that are in less than 5 microseconds, and we will busy wait on the initiator waiting for a response up to that period of time, and then it will actually yield. And so moving more towards an MPI-style busy wait as opposed to our event-based messaging. We actually stall the hardware thread on whatever intrinsic is available on the platform in mwait if we're on one of our Spark systems, upcoming Spark systems, and we'll use an Intel pause instruction and loop checking status in user mode. Something else that we're doing is we're actually going to start using RDMA as it was intended to be used, not as a messaging system, but literally so we can just read remote host memory and we can write remote host memory. And so we're introducing a new model inside of Oracle which gets away from messaging altogether, and that is this remote memory access model. Very similar to open shared memory, but a much more constrained, much more limited, restricted implementation of it. And the model is that is completely transparent to the consumers of the interface that is actually using RDMA or any type of primitive like that underneath of it. So the clients actually see a data structure. They declare a data structure and initialize with the RMA system this data structure, and then they use a set of barriers, and there's a series of barriers that they can use to access that data structure. But basically the model is clients operate on a data structure, and it's transparent to them where the location of the data structure is. Could be on a local node, could be on any one of the remote nodes in the cluster, but once they declare the type of access they need from that structure and implement a barrier, they can then access the structure as though it's local on their system. They do local memory references, and then they say that they're done. So the very same code runs on every node in the cluster. It's completely unaware where the location of the data is. Underneath of it, it's using RDMA operations. It's making that data structure appear locally, or it's updating the data structure remotely, and it's doing it completely silently. And inside of these barriers is where we're doing our busy waits. That's a completely different programming model for Oracle. It basically changes everything. So today, if you're going to program in a cluster in Oracle, you're thinking of millisecond response times. You're not thinking of 10 microseconds or even 100 microseconds. Those are luxuries. 200 microseconds would be fantastic. It's a millisecond because we have to send a message to a process that's got 30 other processes in front of it. And so it can't respond until those guys get out of the way. With RDMA and with these primitives, we can just directly access the memory, and we can share state. We can actually send messages. We'll talk about a messaging system that we're building with RDMA that uses these same primitives. So it's a very big model shift. Now we're actually going to use RDMA as it's intended. And it's generating a lot of excitement because now you have folks thinking about, hey, I can do an RDMA in 2 microseconds. I can pull data or push data in 2 microseconds. That's a big mindset change for the cluster programmers, right? Folks trying to share a state around in the cluster. And so we think that it's going to be a big change in terms of how Oracle performs and how Oracle scales in a large number of nodes. Consistent read, I'll talk about some of the primitives that we do just quickly, but the idea of consistent read is you really want to be able to read memory even though the remote host is actually concurrently updating it, because you don't want to do those expensive serialization primitives. That just slows everything down. I think somebody had a good presentation on that. That just really means slow things down when you have to serialize. So we want to be able to consistently read the data, and we want to be able to consistently update data while another host is actually reading locally the data. So one of the next things we're doing is also adding kind of a partitioned global address space. Again, it's a very restricted implementation of it. Here, all of the nodes in a cluster hand out a segment of their address space in shared memory. It's the same size segment. They don't have to be at the same address location, but they all can access each other's segment, and we can create data structures in that segment, and then we can perform these RMA primitives on them, with just offsets into those segments. So remote memory access helps with a lot of problems that we have today. But it's really, if you look at the bigger picture, it's only a subset of the problems that we have today. Because we're a time-sharing environment, from a scalability perspective, we have to access data on different nodes. And oftentimes, just getting a picture of the data is good enough. Or just sending an update of data that we have is good enough. I'm just about done. It should work out. But a lot of times, you really want to do a little bit more. A little more sophisticated processing. It's like you want a complex RDMA, or you want a custom atomic. You want to be able to not just read the data, you want to look at the data and make a decision on it. And you want to do it in a way that's decoupled from the target processor, the target host system, because it's heavily CPU loaded. Memory bus is heavily loaded. So you want to be able to do these operations without using just a sequence of RMA operations, because it would still be too long. It would take you 20 microseconds to RDMA, and we've done it. We've actually executed these. You read the data, massage the data, write the data back. It'll take you 20 microseconds to complete that, and you can't busy wait for that long. So where we'd like to see things go is to be able to offload some intelligence into future NICs. We want to be able to put a procedure in that NIC. It's a very simple procedure. We're not going to compute pi. We're not going to do anything fancy. It's going to read a very small amount of data, maybe 256 bytes of data from host memory into the NIC. We're going to do some simple processing on it, search it as a hash tree, find that something doesn't exist. We're going to insert some memory in it, a structure in it, write the chunk back, and send back a response. It's pretty much what we want to be able to do. And so we've done some investigation into that, and in theory, we think we should be able to do this in less than 5 microseconds. So having this capability greatly enhances what we can do in a cluster in our synchronization primitives and distributed state sharing. So we're hoping to see something like that in the future, something that has some sort of embedded processing in it, some way of doing debugging, tracing, managing the endpoints, some way to create these procedures, get them into these NICs, and then, of course, invoke them. And so that's pretty much it. Any questions?
The Sumanta slide, there was something mentioned on there about extended verbs for allowing FMR. Was that for the user space?
Yes. Yes.
Is that code available, or could it be available?
Yes.
Absolutely.
Yeah.
Have a usage model for it?
Yeah, we have a patch. We've actually sent it to Tiperet, and so it's available.
So Tiperet said that it is going to be available 1.6.
Yeah, they were going to put it in 1.6. If I could get a copy of it earlier, I would appreciate it.
Yeah.
No problem.
No problem. Yeah, sure.
Okay, I'll talk to you.
Just a quick one here. I downloaded OFED 1.6 and tried to compile it.
Yeah, we're just starting OFED 1.6. Very early. I'm just starting.
Yeah. Yes. Okay. I have a question in the back, please.
How would the Oracle RDMA model deal with the case where the fails and loses memory?
The question was that how does Oracle RDMA or RMA deal with the case when a node fails?
Are you replicating the memory or what?
No. The memory is not replicated. However, the consistent image of memory is always on disk, right? So there is there's recovery involved in it, but as such, there is no loss of data.
So if I go right, are you logging that to disk or?
Yeah. So everything is transactional, and you have the ACID properties.
I have one other follow-up question on your user space FMR. Do you have a time of how long it takes to do user space FMR? How many microseconds or how long?
Yeah.
Only indirectly. It's microsecond or 2 microseconds. It's extremely small. We use FMRs for everything, right?
Yeah.
We do 8K IOs. We'll we'll do the registration, do the 8K IO, and unregister at the end of it. On a typical 20 microsecond IO, it adds about 10% is what we typically see to run FMR, versus if you just kept statically registered and did the same IO, it adds about 10%. It's very cheap to do.
Okay,